All right, let's get started with 1.5. First thing I want to say is after spending all day making the 1.4 videos, those came out way too long. I guess I like linear algebra and I like talking about linear algebra and I think of something to say about something and I can't help myself from saying it because 1.4 was an important section. That's stuff you should know, but I think I repeated myself too much, showing too much work. I learned my lesson. I'm gonna try to make this one less than half as long. We're gonna keep it tight and quick here if I can. So yeah, 1.5 is about subspaces of Rn. Rn or Rc or whatever you call it is called a vector space. And we're going to look later on in like chapter 7 what is the formal definition of a vector space in general, but basically it's a collection of vectors that satisfy some properties. A subspace is a subset of a vector space that but we're just talking about Rn. So a subspace U of Rn satisfies these properties. It has to have the zero vector in it. The subspace U also has to meet property 2, which says if P and Q are two vectors in U, then their sum is also in U. So we say U is closed under addition. Kind of the word closed here means you cannot get out of U by adding two vectors in it. Sort of like how a room can be closed under walking, the same idea. Um, if you can get out of a room, it means the room is open, but if all the doors are closed, the room is closed. Same idea with part 3, but with scalar multiplication. If you have any vector in U and any scalar, then the product of that vector and scalar needs to also be in U. So you cannot get out of the subspace U by multiplying vectors by scalars. So we say it's closed under the operation of scalar multiplication. All right, let's look at a first example here. We want to show that the set U that just contains the single vector 0 is a subspace of Rn. This is called the trivial subspace. All right, so we just need to show that it meets these 3 criteria. The first one is that the 0 vector is in it. Yep, okay, it's right there. There it is. Definitely meets that. That's the only vector in it. To show that it meets condition number 2, we want to say, like, suppose that you have any two vectors that are in this set. So if P and Q are in this set, that means they're both 0. And if we add them together, it's just 0 plus 0. And that is still in the set that contains 0. Likewise, if you take any vector P and any scalar C, and you multiply them, but the vector P is in the set, then C times P is still going to be 0. So yeah, multiplying 0 by a scalar keeps it as 0, so you cannot get out of the set by multiplying 0 by a scalar. You can't get out of it by doing 0 plus 0, so it is closed under these two operations, and that makes it a subspace. So that is the simplest subspace. Let's talk a little bit about the term subset, because the regular English word subset sometimes means something a little stronger than in math. So in math, we say that a set V is a subset of W if everything in V is also in W. And that means W is a subset of itself because everything in W is also in W. That's a little different from the regular English word subset, which often means like a strictly smaller subset, what we call in math a proper subset. So if V is a proper subset, that means there's something in W but not V. So a proper subset is a little bit smaller than the bigger set. So we can say that U equals Rn is a subset of Rn because everything in U is also in Rn. So it's like the biggest possible subset. Okay, so we want to show that it meets the three conditions, and this is really straightforward because 0 is in U, is in Rn, right? And if you take any two Rn vectors, then their sum is also an Rn vector, right? And likewise, if you multiply a vector by a scalar, it's still an Rn vector. Okay, so yeah, it meets all three criteria. This is example 1 here. This is the smallest possible subspace of Rn, and Rn itself is the biggest possible subspace. So those two subspaces are not very interesting. The interesting stuff is stuff that is in between. Let's look at example 3. So M is the set of vectors of the form A, B, C such that A times B times C equals 0. And it's definitely a subset of R3 because we're talking about R3 vectors. But the question is, does it meet all three of these conditions? I recommend trying to think about this on your own for a minute. See if you can show that it's a subspace or not, and then I'll show you my answer here. So first of all, it does meet the first condition that the 0 vector is in M because when you multiply the three components, you just get 0, so it meets the condition. The second thing is if you take any two vectors where this is true, does it necessarily mean that their sum is also true? So in other words, if you have a point A, B, C that's in M, and another point X, Y, Z that's in M, and then you add those two vectors together, you would get the point A plus X, B plus Y, C plus Z. And the answer to this is no. Here's a counterexample. Oh, that's not a counterexample. Let me try again. So here's a counterexample. 1 times 0 is 0, and likewise 0 times 12 times 5 is also 0. But if you add these together, you get the vector 1, 12, 5, and that is not in M. So this is not closed under addition, and that means it's not a subspace because it has to meet all three criteria. And if you can find a single counterexample, that means it's not a subspace. Cool beans. Let's look at example 4. So here we have the set of vectors A, B, C such that when you add their components together, you get 0. Okay. So at first glance, it looks quite similar to the last one. Again, I recommend pausing it and see if you can find a counterexample. Maybe make a guess at whether you think it's a subspace or not. But let's see. Let's check here. So first of all, is 0 in this? Yes. Okay, so it meets condition 1. Does it meet condition 2? So if we have A, B, C, and X, Y, Z that are in P, so in other words, if A plus B plus C equals 0, and X plus Y plus Z equals 0, That means we have two vectors that are in P. Does that guarantee that their sum is also in P? And their sum has components a plus x and b plus y and c plus z. And the answer to that is yes, because you could just rearrange the terms. So it is closed under vector addition. Is it closed under scalar multiplication? So if we have any ABC vector that is in here, and you multiply that by a scalar, the question is k times that vector in P? In other words, is ka plus kb plus kc equal to 0? And the answer is yes, because you could factor out the k. And we assumed that a plus b plus c is 0. So this is a subspace of R3. Sounds good. Let's take a little break right now, and we'll look at a couple theorems to look at specific kinds of subspaces, null spaces, and spans in a bit.